Hello, everyone. Thank you for joining us today, and welcome to the Astro 3D ECR Astronomers in Australia seminar series. My name is Dr. Jeffrey Simpson. I'm a postdoc at the University of New South Wales in Sydney, Australia. And my co-chair is Dr. Marion Gerard from Swinburne University of Technology in Melbourne, Australia. Before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded land on which we're meeting today. I'm speaking with you today from the land of the Wallumedegal clan. My co-chair Marianne is joining us from the land of the Wiradjuri people of the Kulin Nation. Our first speaker, Dana Horta, is speaking to you from the country of the Turrbal and Jagara people. And our second speaker, Arthur Puls, is speaking from Ngunnawal country. We pay respects to their elders, past and present, and extend that respect to all First Peoples joining us here today. So why are we here? This is a series of seminars that's been facilitated by Astro 3D, the Australian Research Council Centre of Excellence for All-Sky Astrophysics in 3 dimensions. COVID-19 has severely affected our ability to travel and present at international seminars this year. This has been especially a problem for us in Australia because we can't travel, you can't travel to us. And although conferences are being run virtually, the time zone differences mean that often meetings are taking place at 2 or 3 in the morning. It's currently 6 o'clock in the morning, so we're doing pretty well here. And this lack of opportunity to network could severely disadvantage junior astronomers when entering the job market. So we're going to have 2 talks this hour. Each talk will be 20 minutes in length with 5 minutes for questions at the end of each talk. Marianne will be the coach will share those question sessions, and please save your questions until the end of each talk. And so also these talks have been recorded and will be placed afterwards on the Astro 3D YouTube channel for educational and scientific purposes. And by being here today, you're agreeing to abide by the Astro 3D's meeting code of conduct. The other last little bit is that I've already warned speakers of this, but because of the limitations of Zoom, I will need to interrupt them sort of verbally with 5 minutes left in each of their talks. So if I suddenly burst in at with 5 minutes left in each talk, that's what's going on. And our second speaker is Arthur Puls, a PhD candidate at the Research School of Astronomy and Astrophysics at the Australian National University. Arthur, the screen is yours.
So can you see the slides? Okay. So good day, everyone. Thanks for the organizers for the opportunity to give this talk. And also thanks for Danny for introducing some concepts that we have in common in our talks. So I'll talk about one of the papers that I'm preparing right now, which is about some metal pore giants in the Kepler field. So recently, the identification of some substructures in the halo allowed by Gaia gave new insights from the perspective of galactic archaeology to understand the formation and evolution of the Milky Way. So in this sense, our goal here is to make an exploratory study combining both the astrometric data with spectroscopy and also the power of the asteroseismology provided by the Kepler mission. So we are talking about red giants. Red giants present solar-like oscillations. They oscillate like the sun. And the characteristics of solar-like oscillations, we can see here the power spectrum of a red giant. And the solar-like oscillations are characterized by this Gaussian shaped envelope. And one of the observables important here is the max, which is the frequency of maximum power in this Gaussian shaped envelope, usually at the center of it. Another quantity that is important is delta nu, which is the average frequency separation between 2 consecutive orders of same angular degree. Here we can see the 0th order, the radial order, the radial degree, the delta nu, the average frequency separation here. Another way to visualize solar-like oscillations is like folding the power spectrum in an HL plot by the frequency of delta nu, that we can see the angular degrees characterized by these ridges in this HL plot. Another useful thing with asteroseismology of red giants is that from the L1 frequencies, we can determine the evolutionary stage of the red giant, either if it's an ascending RGB or if it's in the core helium burning phase, by analyzing this forest of L1 frequencies. Going back to delta nu and nu max, they are related to some fundamental properties of the stars. This can be shown from first principles. Properties such as mass, radii, and surface gravity. And in the case of red giants, knowing the mass is important because in red giants, mass is a good proxy for age. So we can have some chronological information from astroseismology in this case. To give some context of this study, back in 2014, Epstein et al., they highlighted a possible inaccuracy in these scaling relations shown in the previous slide, at least for red giants in the metal pore regime. Here, it's one of their plots showing the masses they calculated for some halo red giants. And we can see here that they're more massive than what was expected for halo red giants that is showing the gray shaded area. Also, other studies from spectroscopic binaries suggested that the scaling relations overestimate the masses of red giants by a few percent. So some kind of correction needs to be applied. And in the last few years, several model-based corrections have been published and adopted in astroseismological studies of red giants. Here's an example, and we can see that the correction on delta nu. Here's the ratio of delta nu, observed delta nu, and model delta nu as function of nu max. Here we can see that the corrections are highly nonlinear in the red giants. So in this study, you observed with Keck, with HIRES, the spectra of 7 of these red giants. From the astroseismology, we know that they are all RGBs. They are not from the red club. And we are combining the spectroscopy with the analysis of dynamics from Gaia and grid-based modeling from astroseismology to determine the fundamental parameters. These metal pore giants, 5 of them come from this study from Epstein 2014, and other 2 are metal pore giants from the Saga survey. So the spectroscopy is the classical spectroscopic method using Crookes models in LTE with the atmospheres constrained by effective temperatures calculated with the infrared flux method, the IRFM, and accurate values of log G from astroseismology, which gives a precision that is, it can be 2 orders of magnitude more precise than the log G from spectroscopy. So you use it as a seismology also to constrain the atmospheric model, use it to calculate the chemical abundances using equivalent widths and spectral synthesis. For the dynamics / kinematics, we use a Gal-Pi fed with Gaia EBR3 data to calculate the actions, angular momenta, orbital energy inclinations, and so on, and those some individual orbital modeling of each of these 7 stars. The grid-based modeling uses the code BASTA that gets a set of observational inputs such as delta nu, nu max, evolutionary stage, effective temperatures and metallicity, and uses a Bayesian approach with MCMC to fit these observables in a set of Basti models. And also it applies corrections to the asteroseismic parameters, so we don't overestimate masses. So the results here, we can see each of these letters correspond to one of the Epstein 2014 stars. The blue stars in the plot are results for both ages and masses. And the gray shaded area is the mass range expected for halo giants if they were formed in situ and if they are very old. So the open black circles are the results in masses from Epstein, and we can see that the masses we calculated here with our grid-based modeling are lower than initially published by Epstein, but still when we compare with the expected mass range, except for star C, they are still more massive, meaning that they are still younger. Even when we use the Epstein 2014 observational data, delta Nuno, max, etc., to fit in the grid-based modeling, the mass values decrease, but their values are less precise than the values we got in our work. So the resulting error bars are too large for making any qualitative assessment using their data. But still, basically what we are showing here is that our results say that the stars are still too massive to be in situ halo stars, especially star B, that the grid-based modeling gave a very young age. So what's happening with star B? From the chemistry, it looks like a classical halo star, a metal poor, alpha enhanced, but the asteroseismic mass is wholly one solar mass, corresponding to an age of 5.5 giga-years. So checking on Gaia EDR3, this star has a Rho value of 2.8. And it has been argued recently in the literature that the astrometric solutions with value of Rho value that deviates too much from 1, they are related to binarity. So that means that star B, it's probably a component of a binary system. And from that, it can be suggested that it's actually an evolved blue straggler that accreted mass from a companion in the past. So it's currently more massive than its initial mass, and being a red giant, this makes the star actually masking its real age. It would be much older than 5.5 giga-years. So from the 2 stars of the Saga survey, one of them we call S1, the grid-based modeling analysis also gave 1 solar mass. We can trust this value because it comes from corrected asteroseismological scaling relations, but we had a problem actually fitting in the isochrones. From the metallicity we calculated in the spectrum, the best solutions should fall here in the left-hand isochrone, but in this case, it's outside the TF range we calculated using the RFM. And when you get a good solution that matches the temperature, then the solution falls on an isochrone that corresponds to a metallicity that is 1 dex more metal rich. Also, this star is a bit complicated because when we do a SED fit, it looks that it has some infrared access from WISE photometry. So someone could argue that the star has a debris disk that would be result of some past merger event. But also we can see here that this gray curve that crosses the model spectrum is the observed flux. So we actually couldn't fit any of the template spectra well for this star. So star could have some problem in the photometry that gave us some wrong temperature. The other star from the Saga survey, it's curious because it has the power spectrum from Kepler has a very low signal to noise ratio because it's in the upper RGB, so it's approaching the resolution limit of Kepler in the frequency space. And when you look at the literature, there are very different delta nu values. They differ by 3 sigma, the values that we found on EU 2018 and in the APOCASC survey. And depending on the delta nu value that we choose, we can get a very young age, shown here in this blue violin plot, or a very old age compatible with the age of the universe. Our adapted value corresponds to the APOCASC 2 delta nu, and this orange violin plot corresponds to the age distribution we calculated. That is similar to the age distribution we calculate if you use also TF and metallicity from APOCASC. So why did we choose APOCASC? Because checking the eshel plots, on the right, we can see the eshel plot with the frequency module using the delta nu value from APOCASC. And we can see the ridges here as it was shown previously in the other slide, and we could visualize the power spectrum. But when we apply a frequency module using the EU 2018 value, the eshel spectra becomes completely messy. So from visual inspection, we assume that the APOCASC 2 value is more accurate.
It's 5 minutes left.
So from the dynamics, what we can take, there is a potential Gaia, Sequoia, Gaia Sausage membership for some of these stars. Their dynamics match in the parameter space, their dynamics match those found for Sequoia/Sausage. For some of the stars, here is shown an action plot with the stars and the shaded areas corresponding to Sequoia and Sausage. And a few of the stars, 3 of them, match in all the dynamical parameters we checked. So when we look at the chemistry, here we have a comparison with a recent paper from Monti et al., where they analyzed pre-selected Sequoia/Sausage stars in the chemical space. So at least in the alpha elements, some of these stars here, they correspond to the fit of the alpha Ni. So we are not claiming that, oh, these stars are members of Sequoia Sausage, but at least in this table, in the green columns, we cannot rule out their membership. So they could be members. The the yellow columns are stars that we don't have enough information to do any qualitative assessment. So we cannot say if they could be or not members. And the red one is that star with not good astrometric solutions. So we simply excluded it from the analysis. So here we can see also the estimated ages of the stars, and the Sequoia/Sausage members are relatively old. And assuming that they are members, for instance, of Sequoia, we can see that one of them is 10 gigayears old and the other is 13 years old. So assuming that they are members and they formed before the accretion event, then we could set a lower limit in the age of the accretion event. So to conclude, this is an exploratory study to check where we can reach by combining the power of Kepler, Gaia, and ground-based high-resolution spectroscopy. One of the important results is that even using model-based corrections, asteroseismology keeps giving masses higher than expected for the Epstein 2014 sample. Actually, one of the motivations for the model-based corrections was the result, but we are still getting masses that are larger than expected. But this is not necessarily a problem if we assume that they could be members of some accreted galaxy. And if they are, we could use them to date with some good precision the accretion events, at least in the age scale we are using here. And finally, the combination of these methods makes easier to, for instance, identify evolved blue stragglers, burst stragglers that are in the right giant branch. And that was my talk, and thanks for your attention.
Thank you, great talk. Again, if there's anyone that have question, you can write it in the chat, or you can also raise your hand and you can unmute and ask the question as well. So anyone has a question?
I'll ask the question. So those blue straggler stars is really interesting because, so I've got a recent paper that's on the archive but hasn't been submitted yet, where we were looking at Gaia Enceladus stars, dwarf stars with Galar, and we noticed that there were a couple of stars that clearly have very Gaia Enceladus-like orbital dynamics, but if you plot them on an HR diagram or a calorimetry diagram, they look like classic blue stragglers. Like they're much more blue, much more hot than you expect for the sequence. So it's interesting. Yeah, so we've seen them as well in Galar. That it's really more a comment than a question. So.
Yeah, actually, there are estimations that in the halo, like 1/5 of the stars would be blue stragglers, and we happen to have 1 or 2 in 7 stars that are blue stragglers. It could be a coincidence, but
yeah, I mean the possibility is that some of these ones are just dynamic, or they've been thrown into the halo-like orbits during accretion events. They aren't necessarily blue stragglers that have been brought in with these accretion events. These particular ones happen to be right on the edge of the energy LZ box.
We have a question on the chat from Ted. So nice work, great talk. We also found many of the overmassive star in the halo in our paper. And sorry, it's not a question, it's a comment, and there's a link there. So if anyone else has a question, please raise their hand or write in the chat. No worries about the comments. Okay, we have another question from Paula. So are these Sequoia candidate stars very eccentric?
Yes, they are. We can see from in the action plot they are color coded by eccentricity. They are between 0.7, 0.8.
Okay. Any other question for Arthur? No, there's a follow-up question, but not all are alpha port, right?
No, they are not alpha port, but at least from the comparison with the literature, they fall in the expected range for what we know from the chemistry of these accreted objects.
Okay, thanks. I probably have time for other question if there's someone else that have a question. Otherwise,
I have one. I just can't raise my hand. Sorry. Great talk, Arthur. I was just wondering, so you know that your summary plot where you have like the memberships and how reliable your memberships are. Could you just skip to that real quick, please? I just want to ask you something on there. Yeah. So your reference H star, right? So this is, I'm guessing this is like your reference thick star, right? So that the properties of that are quite similar to your D star, right? I was just wondering how do you distinguish these things? Is that because of like its chemical composition or its integrals of motion? What makes them different?
I don't know if I understood exactly your question.
Sorry, I'll rephrase it. Okay, so your D star, right? So if you look at the properties at the bottom, so it's iron and age and stuff, and your H star, this might be a really silly question, but it's the difference between these two basically the integrals of motion and chemical properties.
Yeah, in the chemical space they are very close, but one is prograde and the other is retrograde.
Okay, sweet. That's it. Thank you.
great. Any last question? I don't see any hand or any question in the chat, so I'll give it to. Thank you again, Arthur, for your talk, and Jeffrey.
So thank you to Danny and Arthur for their great talks. I've certainly learned a lot.